Our understanding of the world is wrong. Cosmology, long the key to explaining the grand architecture of the universe, is facing a major debate over one of its most important questions. How fast is the universe expanding? For more than a decade, two sets of measurements have puzzled astronomers. On the one hand, current global observations show an expansion rate that appears to be 9% faster than predictions based on historical global data. This troubling discrepancy sparked a huge debate and sent scientists searching for answers, even as they turned to the James Webb Space Telescope, JWST, the most advanced observatory instrument ever built, to find out. But instead of explaining, JWST's precision only deepens the mystery. The difference between the measures, now measured and precise, continues to challenge the standard model of internationalization, a concept that is more than 40 years old. As scientists gather to discuss the implications, a more important question than ever arises. Is there something deeper about our understanding of the universe? Join us as we explore puzzling observations that suggest something is seriously wrong with our understanding of the universe, thanks to deep JWST images. The story of our world begins with an explosion, a big explosion. In short, energy, mass, and space are created. From then on, the world began to expand as a sign of the future. The young world was a turbulent, chaotic plasma, a pulsating mass of particles and antimatter particles that only collided to destroy each other when they collided. Left to their own devices, all matter and antimatter must consume each other, leaving nothing. However, due to imbalance, however mysterious, matter can triumph over matter and prevent the universe from destroying itself soon after its creation. When this plasma eventually cooled, the force could work its magic, compressing the primordial world into voids of matter. In these cavities, sound waves, called baryon acoustic oscillations, ripple through the surface of the hot plasma, traveling at only half the speed of light. These oscillations helped shape the world into the vast World Wide Web we see today. At the same time, the physical and dynamic elements of the universe will arrive and reshape the fabric of space. As the world expands like a balloon, it begins to gather away into dense clusters of invisible dark matter. Galaxies slow down in these orbits, connected by strings of dark matter around the universe. Over time, as matter expands, the universe's expansion slows down, reducing the amount of energy in the process. But about 5 billion years ago, something unexpected happened. The universe began to expand again, thanks to a strange and mysterious force called dark energy. The simplest definition of dark energy is a constant, an incremental force woven into the fabric of space. This mysterious force, first introduced by Albert Einstein in his general theory of relativity, is called lambda, and it works the same way throughout the world. It is always there and pushed out by encouraging world expansion. As the universe expands and the density of normal and dark matter decreases, the influence of dark energy becomes stronger and becomes the dominant force driving the universe's expansion. The energy density of normal matter, dark matter, and light combined with dark energy to set an upper limit for the expansion of the universe. This theory is the backbone of the lambda cold dark matter model, lambda CDM, the standard planetary model that describes the formation and evolution of the universe. According to the lambda CDM model, the universe will continue to grow forever, with the distance reaching a point where it will reach a heat death, or ice mass, where all energy is distributed and no useful energy remains to be conserved. The existence or movement of this model has produced many accurate predictions and shown global growth with great accuracy. However, despite its success, it rests on several assumptions that have never been fully understood. Dark matter and dark energy make up the vast majority of the universe's content, 25% and 70%, respectively, while the ordinary matter we can observe constitutes a mere 5%. Yet, despite their overwhelming influence, astronomers still have no concrete understanding of what dark matter and dark energy actually are. Ofer Lahav, a professor of astronomy at University College London and a key figure in galaxy surveys of dark energy, described this uncomfortable reality succinctly. The embarrassing fact is, we don't understand the last two of them. Despite decades of research, dark matter and dark energy remain elusive mysteries, casting a shadow over our understanding of the universe. And now, a new threat to the lambda CDM model has emerged: one that strikes at the very heart of cosmology. Depending on the method used to measure the universe's expansion rate, scientists have different answers. This difference is known as the Hubble tension and represents one of the biggest challenges to the standard model today. To understand the Hubble voltage, we need to know how astronomers measure the universe's expansion. The rate at which galaxies move relative to each other is called Hubble's constant, named after the famous astronomer Edwin Hubble, who first observed the expansion of the universe. For decades, scientists have relied on two main methods to measure this constant, but these two methods have produced conflicting results. The first method looks deep into the past and measures the universe's expansion rate using the cosmic microwave background, CMB, the glow of radiation left over from the Big Bang. The CMB is a snapshot of the universe as it existed only 380,000 years after the Big Bang, when the ocean of hot plasma was the same. The small temperature variations in this early world show how matter combined to form the large-scale structures we see. Between 2009 and 2013, the European Space Agency's Planck satellite produced the most accurate CMB map to date, measuring the Hubble constant with an uncertainty of less than 1%. According to Planck's observations, the Hubble constant should be about 67 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, that the galaxy moves away from us, it must slow down by 67 kilometers per second. But there is a problem. Another method of measuring the Hubble constant uses objects that are very close, shooting stars known as Cepheid galaxies. These stars grow and shrink in size, causing their brightness to fluctuate in a predictable way. By measuring how long it takes for a Cepheid to complete one cycle of brightening and dimming, astronomers can determine its true brightness and, by comparing that to how bright it appears from Earth, calculate its distance. This method has been used to build what is known as the cosmic distance ladder, allowing astronomers to measure distances to faraway galaxies and, by extension, determine the universe's expansion rate. In 2019, a team led by Nobel laureate Adam Rees used the Hubble Space Telescope to measure Cepheid variables in a neighboring galaxy, the Large Magellanic Cloud. Their results were shocking. They found a Hubble constant of 74 kilometers per second per megaparsec, significantly higher than the value predicted by the Planck satellite. The difference between these two processes, known as the Hubble problem, has become a growing concern in recent years. Because of the huge difference between the two reliable methods of measuring the universe's diameter, astronomers hoped that the James Webb Space Telescope, JWST, could provide the final information. Launched in December 2021, JWST represents the pinnacle of observational technology, with a mirror nearly 3 times the size of the Hubble Space Telescope and the ability to detect objects 100 times fainter. Additionally, its infrared capabilities allow it to see through dust and gas, revealing new information about distant stars and galaxies. Because of its precision, astronomers hoped that JWST would solve the Hubble problem once and for all. Instead, it only confirmed the situation. Rice and his team used JWST to measure Cepheid variables in the galaxy NGC 4258 and compare them to Type Ia supernovae. Their results were consistent with previous observations, a Hubble constant of 73 kilometers per second per megaparsec. Other independent measurements, including those by Wendy Friedman's team at the University of Chicago and observations of the brightness of red giant stars, have also yielded higher values for the Hubble constant. However, astronomers observe, the universe appears to be moving faster than the lambda-CDM model predicted. The tension between these two dimensions has puzzled astronomers. A difference of 7 kilometers per second per megaparsec seems small, but in the world of the universe, it is very important. Rees says, "The only reason I can see right now that they don't agree is that something is wrong. The implications of the Hubble problem are profound. If the current model of the planet cannot explain this difference, it must be revised or replaced."